Alright, so in this video, I want to give the corollary to Fermat's result about which primes are sums of two squares, which is this beautiful theorem that reads as follows. Any number n is a sum of two squares if and only if, when you look at its prime factorization, all the primes that are 3 mod 4 in the factorization, well, if there were no primes that are 3 mod 4, we would automatically know it because we know primes 1 mod 4 are sums of two squares, and we have that earlier proposition about products of sums of two squares or products of sums of two squares. So if there were no primes that were 3 mod 4, you would know you had something that's a sum of two squares, but we're also allowed to have primes that are 3 mod 4 showing up in the factorization, but they have to have even exponent, right? The other case that we've seen so far that this includes is primes that are 3 mod 4. Those are just like a prime to the 1, so that's an odd exponent case. Those are not sums of two squares. So this gives you a result for every single integer, right? So if you wanted to know like how many, you could start asking questions given this, like how many numbers up to a big bound are sums of two squares, etc. You could attack problems like that maybe. Or if I hand you number n, as long as you can write down the prime factorization, you have an algorithm to quickly test whether it's a sum of two squares without actually having to run through all the possible numbers, and it's a nice, beautiful characterization. All right, great. So let's prove this. So we've done the hard part, well, that's why it's a corollary, but there's still a little bit of work to it. All right? Okay, so it's an if and only if, so we have to prove both directions. So one direction is if everything in all the primes that are 3 mod 4 have even exponent. Okay? So let's write right implies left. If all primes that are 3 mod 4 show up to even exponent in n, then we have to show it's a sum of two squares. So if all primes are to even exponents, so this is all primes congruent to 3 mod 4, right? If these are all to even exponents, then, right, the part of the prime factorization of n that involves things that are 3 mod 4 is a perfect square, right? So that's what we're going to use. So then say, let's factor n as t squared times u, where u is square free, right? So you can always, as we've talked about, you can always factor any number. You can take the primes that have even and odd exponent. You can shove all the ones with even exponent into a single number, which is then a perfect square. And so you can always write something as a square times a square free number. T is the product of all the primes that occur to even exponent, but then take the square root, use all the rest of the stuff. But all the even exponent stuff, all the stuff that's 3 mod 4, all the primes that are 3 mod 4 lie in the t part. So we know that u has no 3 mod 4 primes. Right, so u is square free, so it's a product of primes that are 1 mod 4, possibly times 2. All right, so we can always do this, and basically the point will be a square, as we talked about before, is in particular a sum of two squares, and we know how to handle products, and u we've handled by Fermat's theorem. All right, so u is a sum of two squares, right, as it's a product of primes p equal to 2 or p congruent to 1 mod 4, and each of those primes are sums of two squares. So each are a square plus a square. Okay, right? So every prime showing up in the factorization of u is a sum of two squares. We've seen that property of being a sum of two squares is preserved under products, so therefore u is a sum of two squares. Right, so t squared equals 0 squared plus t squared is a sum of two squares, right? Just because every square is a sum of two squares. And so again, by the multiplication fact, that lemma or that algebraic identity, u times t squared, that's a product of two sums of two squares, which is equal to n. By their definition, this is a sum of two squares. All right, so basically it follows just kind of directly. If you just write it out based on what we did, the right implies left direction. All right. So the other direction is that if n is a sum of two squares, that it has all primes that are 3 mod 4 in its factorization. All of them are occur to even exponents. All right. All right. So let's do right implies left. And we'll basically do this like by contrapositive. So that's if n is the sum of two squares, everything that's 3 mod 4 occurs to even exponent, right? The contrapositive is not everything occurs to even exponent. Implies is not a sum of two squares, right? So contrapositive is not everything has even exponent. That means there's at least one thing with odd exponent. So say p is a prime that's congruent to 3 mod 4, and p divides n with it has even odd exponent. So I'll say p to the 2j plus 1 is exactly the exponent, right? So p to the 2j plus 1 exactly divides n. Okay. So the contrapositive is then that if I have such a prime occurring, then the goal is show that n is not a sum of two squares. All right. So let's do this. So it's going to be a proof by contradiction. So we're going to prove this by contrapositive, and then the contrapositive we prove by contradiction. So suppose n is the sum of two squares. Say it's x squared plus y squared. All right. All right. So in this situation, so we have p is a prime that's 3 mod 4. It divides a number n that's the sum of two squares to an odd exponent 2j plus 1. All right. So now we kind of factor out stuff out of this equation. We clear out common factors. So let's say that x and y, I don't know if they're co-prime. But let's say their GCD is d, right? I can divide the whole equation out by d, right? So I can divide, if I let a is x over d and b is y over d, these are both integers, right? So when I take these guys squared and add it up, I get x squared plus y squared all over d, which is n squared over d, right? So I'm going to let n over d squared. So let m equal n over d squared, right? And then this equation becomes now a new equation in integers, m squared equals a squared plus b squared, right? And I divided through by the common divisor, the common factor, the GCD in x and y. So a and b are by choice now relatively prime. Okay, great. So now I have a new equation of something as a sum of two squares where these two things are co-prime. All right, so that's what I'm going to use. And let's say that, well, some power of p could divide d. So everything's about studying the power of p dividing stuff. So some power of p could divide. So let's say that it divides it k times. So let's say p to the k exactly divides d, right? Then I look at m. So then, well, I have that p shows up in n 2j plus 1 times. N over d squared is still an integer. So if I look at the power of p that divides n over d squared, I at least have the power in n, 2j plus 1, minus twice this thing that shows up in the d, because that's a d squared in the denominator. So I have that p to the 2j plus 1 minus 2k divides m, my new thing here. And this should not have a square here, right? M is a sum of two squares, just like n was a sum of two squares. All right, so now I look at this exponent, right? Now we use a parity argument. So I've just argued for you that this is greater than or equal to 0, right? That this actually does divide, and you know, at 2k p, when I divide all these powers of p, I'm still left with an integer. M is still an integer because a and b are integers, right? And m is a squared plus b squared. So this exponent of p here is greater than or equal to 0. But it's also an odd number. So this is a really handy trick a lot of the time. Whenever you have an odd non-negative number, it has to be positive, right? So this exponent is 2j plus 1 minus 2k, so that's odd. And it's greater than or equal to 0. And every odd number that's non-negative is in fact greater than 0. Okay? So this exponent is greater than 0, so p to a positive power divides m, and that means in particular that at least p divides m. Okay, so that's a key fact we're going to use soon. Okay, so I claim that p does not divide a, right? So now p does not divide a, as else Well, p divides a, we just saw p divides m, so p divides b squared implies p divides b. So else p divides b, and that's a contradiction because the GCD of a and b is 1. All right? Okay, so this contradicts ab equals 1. Okay, and so this means there exists a z solving the equation because a and b are invertible mod p now, right? So we can solve the equation az is congruent to b mod p. See? So we're going to pick a z that solves that. All right, so let's back up now. So we'll use this z. So like we have this equation. Where's the one we want? We have n is x squared plus y squared, m is a squared plus b squared, and now we have a relationship between a and b. So we still have our n is x squared plus y squared, our m is a squared plus b squared, but a is related to b, right? So this means that, a squared plus b squared, let's plug in. B is really congruent mod p to az. So this is a squared plus az all squared, right, which is congruent to, I have an a squared as a common factor times 1 plus z squared. Okay, so this is all mod p. All right, so I have this equation, right, and a squared plus b squared equals m, and p divides m. So a squared plus b squared is m, p divides m, right? So therefore, this is congruent to 0 mod p. All right? Because this is a squared plus b squared, right? That's equal, let's just write it this way. That's equal to m. M is a multiple of p. So this is all congruent to 0 in the same chain of equations. Okay? So therefore, I can erase this now. Let me just write first and last terms one more time. 0 is congruent to a squared times 1 plus z squared mod p. But we also have, somewhere we wrote it here, p does not divide a. So p divides either a squared or 1 plus z squared. You can't divide a squared because a is co-prime to p. So that means that 1 plus z squared is congruent to 0 mod p. Right? And if 1 plus z squared is congruent to 0 mod p, well, we can solve and say that minus 1 is congruent to z squared mod p for some z, right? And that means that minus 1 above p is equal to plus 1, right? Minus 1 is a quadratic residue mod p, but p was 3 mod 4, so this is a contradiction. That makes no sense. All right? Okay, so that's it. That's the characterization for sums of two squares. It's a very beautiful classical result. By the way, looking at, when is a prime equal to x squared plus y squared, that's the case that we've done. If you vary this problem slightly, you get lots of interesting stuff. So, in fact, there's an entire book called, literally the title of the book is Primes of the Form x squared plus ny squared. Literally, there's a whole book that you would have to do a couple years of graduate mathematics in order to understand how to solve this equation in general. That takes you on a tour through a lot of the biggest theories in mathematics, and you need the full structure of something called the theory of complex multiplication, which, although it's a funny name, it's not really just multiplying complex numbers. But anyway, that theory is what the great mathematician Hilbert once called not only the most beautiful theory in all of mathematics, but the most beautiful theory in all of the sciences. And it's needed just to study. So if I just took n to be a couple other values, you could imagine there's a couple other ones that are easy. But studying Diophantine equations like this, where you have primes, that's a really, really hard problem. So you could ask many, many other questions, like instead of a prime, I could say, when is like a number a equal to something like this? When is a equal to a sum of squares times numbers, etc.? Those types of questions get very interesting very quickly. Again, Bhargava is one of the shining lights in this area of studying representations of numbers by these type of, we call these quadratic forms. Anyway, this is a very big and beautiful topic of mathematics, and we're just kind of touching the surface here. And what remains to do today is we want to talk about when are things sums of four squares, and the amazing result, the famous result, is that actually everything is a sum of four squares.